Hello everyone, I'm Shubhang Bhatnagar and this is Abhiraj and we both are members of Group 9 and we are going to present today on scattering invariant deep convolution networks, which is an application of multi-resolution wavelet based methods in uh, deep learning. As we know, convolutional neural networks have convolutional neural networks have actually brought a huge revolution in the field of computer vision and image processing, and even in other fields of machine learning. And they are extremely uninterpretable. It's not understood what causes them to work so well, and they are basically based mostly on empirical evidence. Most of their hyperparameters or their models are selected using anecdotal and empirical observations. So we try to answer the questions and try to interpret deep neural networks and CNNs by using wavelet transforms, specifically using scattering transforms. We explore a paper by Stephen Balat, which tries using a specific wavelet network called a specific wavelet transform called scattering wavelet transforms uh, to augment the power of CNN, and it observe that how beneficial can it be to use a wavelet network, a wavelet head before a CNN, and it also brings in some iota of interpretability in CNNs. uh, Abhiraj will now take over and guide through the background.
Yeah, yeah. So first, let's go through the background of the convolutional neural networks and the wavelet scattering transform. So traditional convolutional networks that are currently used and which have the state of the art in various classification as well as detection tasks for vision, they basically can be represented using a simple represented as follows, which where XL is basically the output of the Lth layer of the CNN, and the convolution itself can be represented as the equation one given over here, where HF is our convolution kernel and XL is the input to it, which was the previous layer's output. And so the L plus 1th layer output can be given by the sigmoid or a non-linearity. Basically this sigma represents a non-linearity applied to that of the output of the convolution. So this is what our standard CNNs were. So now we'll take a look at wavelet scattering transform. So the 2D wavelet scattering transform, a 2D wavelet transform can be the mother wavelet of that particular 2D wavelet can be represented by this equation 3, where our where R is a rotation matrix and J are the indices which are used for the scaling the wavelet. So in the 2D we have these two directions that in which we can dilate our wavelet and also rotate and as well as translate. So these three things can be done in a 2D. So now our the conventional wavelet, what the wavelet conventional wavelet transforms does is key it convolves this wavelet that we have with that of our the input signal that we have, which is XCU in our case. And uh, what different that is being done in scattering wavelet scattering transform is that along with this convolution with the wavelet, we are also doing a convolution with the psi j, which is basically an averaging function, or in other words, it's basically a low pass filter, which only preserves our low frequency low frequency information that is present in the signal. So now uh, uh, after this, what the wavelet scattering transform does is it takes the modulus of this wavelet convolution with the input, and then after taking the convolution, so after taking the modulus of that, we again perform the convolution with the wavelet on this modulus that we took. So if we define our mu lambda of x as x convolved with psi lambda, psi being the wavelet, lambda representing the parameters. So by parameters, I over here I mean the j's and k's that we have for rotation and scaling. So if we represent our convolution, the mod of our convolution as this, then for a particular path, path P, which will be given by all the different parameters that parameters of the convolution of the wavelet that we can take, we can define the modulus propagator in the following manner, where we iteratively convolve with a wavelet and then again take a modulus. So this basically form the basis of this wavelet scattering transform, and the scattering coefficients are then obtained by convolving this convolving the modulus propagator with that of the low pass filter that we have, the psi j, which was defined before over here. And yeah, so finally we get this wavelet scattering coefficients. And the good thing about these wavelet scattering coefficients is that they are quite robust in nature, and by robustness I mean they are translation invariant, rotation invariant, and and also deformation invariant, which is the key property which has been used by the main one of the main references of our reflection paper, the invariant wavelet scattering convolution network. So yeah, this basically completes the background of wavelets and wavelet scattering transform and the CNN. Let's move to the summary of the two papers. So the first paper, the scattering invariant convolution network, it proposes a good classifier basically should first of all give us good feature representations. So this to obtain good feature representations, in invariance to the changes in the within the classes is highly important, and these invariances can be of three types. One is translation invariance, additive noise invariance, and third is invariance to the deformation. These can be mathematically written as follows, where phi is our feature extractor and x is the input. So for a good feature extractor, we expect that it expect that the uh, difference between the perturbed input and that feature of a perturbed input and that of the original input is smaller than a constant times the perturbation itself. So similarly, similar is followed in that of a deformation, where tau basically defines our deformation function. So so yeah, so the tradix first the major thing that the this paper talks about is the difference between the traditional techniques and that of the current technique. So the traditional techniques, the Fourier modulus, autocorrelation, and registration, show very strong invariance to that of translation and additive noise, but that's not the case with that of the deformation. As for high frequency, they become very unstable, and that is what is novel about scattering transform, that even in high frequency it is still stable to the deformations that are happening because of the that happen, sorry. Yeah. And yeah, so but the important thing is the wavelet transform itself it, it itself is not translation invariant, and the convolution operation also is also itself not translation invariant, it's translation covariant. So to make it translation invariant operations, three things need to be done. First is to take the average. So by averaging by performing the average, we are sort of creating a invariant from a quantity which we know is not invariant to a particular not invariant to the uh, div- uh, not invariant to translations. But it turns out just integrating the wavelet convolution gives us zero. So we basically need to have a non-linearity, and the non-linearity that needs to be chosen should be a very specific type of a non-linearity, which should basically be stable to deformations, should be non-expansive in nature, and also should preserve the signal energy. And the only thing which satisfies all of these three is the modulus operator, and thus the modulus operator has been chosen in this paper. So this is basically exactly what we get in the scattering transform as well. That's why we are calling it as scattering invariant convolution network. Now, on the implementation side, this implementation can be seen by this particular diagram over here. So if we have our first input here, the outputs are corresponding convolution with all the psi lambdas that we have, then which gives us the first layer. Then they are averaged to get our scattering coefficients. Similarly, on the first layer of the network as well, and then we perform the same operation on the first layer to get our second layer, and then average to get our scattering coefficient, which are basically the output of our network, and those form the feature vectors for our input images. Moving on to the results, important thing can be seen over here is that key it performs it gets state of the art results on almost all the training sizes that we use, and among all the different models that are compared. And also, if we have a look over here for different two textures over here, so this one was for MNIST dataset, and this is for the Curate dataset. So if we have two different textures, then first one is the Fourier modulus. So these are quite similar. Second one is the first layer output of our convolution scattering network, and third one is the our second layer output of the network. So these two are very comparable, but second layer basically shows us that basically gives us a differentiator between these two images, which is not given by the Fourier modulus operator. So this is just an example of that. Now, yeah, Shubham, please continue with the learnable scatter nets.
Uh, so in the first one, in what Abhiraj summarized right now, we learned that the scatternet can provide very useful features which are invariant to various kinds of perturbations. But is it appropriate to apply the scatternet and apply and extract features directly from the images? In many applications, it might be necessary to pre-process the images before taking a scattering wavelet transform. Also, why do we have a scatternet as a fixed block in the network? Can we also fine tune it to adapt to several different kinds of images we are going to use this for? Because the scatternet is a constant transform which might benefit from some kind of fine tuning done as per the domain of the image being used. So in this paper, the authors first they introduced two trainable parameters A and B, such that so that so in as given in this equation, and these trainable parameters A and B help adjust the amount of the amount of different help adjust the weights given to the different components of the scattering transform. And these B and A and B are learnable parameters which can be varied, and they can help give different weightages to different scales of processing in the transform. And additionally, the authors also can you just scroll a bit above to the diagram? Yeah, the authors also introduce a layer before applying the scattering transform. They introduce a convolutional layer at the beginning. The image first goes into a convolution layer which is learnable, and then a scatternet transform is taken. It is hypothesized that the initial convolutional layer will help pre-process the image and help the scatternet, which is also fine-tuned, learn in a better way. Can you scroll down a bit? So yeah, the the good thing about this modification is that even if these parameters are learnable, the original scattering transform can be easily recovered by choosing A and B, by choosing specific values of A and B, and choosing a ReLU non-linearity, which is the most commonly used non-linearity in convolutional neural networks. So the implementation of this, for implementing this, they use the discrete time continuous wavelet transform, and this helps them. They use it in a they use it they calculate it by separating it among the two dimensions, which leads to much higher computational efficiencies compared to standard convolutional networks. They have they analyze their network for the number of trainable parameters as compared to a standard convolutional network, and the number of parameters in such a learnable scatternet based uh, neural network, which although is learnable, is much lesser than the number of parameters in a full convolutional network. And the number of computations done here for getting an inference from a learnable scatternet is also much lesser than a full convolutional network, as you can see in this table. So the authors provide calculations for the same, and they show that their architecture requires much fewer parameters and much fewer computation, and still performs almost as good as other fully convolutional architectures, which do not make use of any wavelet transform or any scatternet, and hence have too many more learnable parameters and much more multiplication, much more computationally inefficient. And uh, so, yeah, Abhiraj, can you take over for the next?
Yeah. So the third paper that we were looking at was called the deep scattering transform, deep scattering spectrum. So this paper was basically from the same author as the first paper, and this is just an extension of the work which is done on the in the first paper to audio signals. So the formulation of the scattering transform and the network that is used in this paper is exactly the same as what was used in the first paper, which was this particular network. But the difference being, in the first paper we were looking at 2D wavelet for 2D wavelets, but in this paper we will be performing our wavelet operations in so in that paper we are performing our wavelet operation in the spatial dimension, but over here our wavelet convolution will be performed in the in the time dimension, and also the second one in the log frequency dimension. So basically this dimension, so if you look at the spectrum over here, then we are performing the wavelet convolution in this dimension, and then the second one in this vertical dimension. So why to do this? The reason is the convolution along time dimension helps us to be uh, robust to deformations in time, which could be time dilation in the signal. And the second operation along the log frequency dimension helps us to be robust to changes in frequencies. So for example, uh, if male says a particular word, compare that to a female, the pitch of a female is much more, it's more than that of a male. So that's what creates difference between these two, and we want our model to be robust to these two when we are classifying. So since they are speaking the same word. So yeah, so they over here they perform the experiments on two data sets, which are for the music genre classification and phone classification as well, which is the GT ZAN and Timid data set. And they claim to have got state of the art accuracies even when compared to the traditional techniques, which is the MFCC technique, which is which is very popular in the audio signal processing domain. Okay, so one thing that I forgot to mention before was that key in all these experiments, they are using the Morlet wavelet, and the expression for which can be seen from uh, uh, yeah, the expression for which is given over here. Yeah. So yeah, now we move on to the possible extensions that we think could be taken from now onwards. And yeah, please Shubham, continue.
Like the scattering transform perform is quite an interesting piece of work, which helps in it is, as we have seen, it is invariant to slight perturbations, and that is a very desirable property which is needed in features, and it can help in a variety of work, including all of these questions. I will first expand on the application of and on the use of scattering transform as an auxiliary self-supervised task. So just a bit of detail about self-supervision. Self-supervision is a type of unsupervised representation learning where we train the network using self-labels which are generated by itself. So we train it on a pretext task without the use of labels. For example, we can train a network to restore a degraded image or a transformed version of an image so that it can model the images or model the distribution of the data without even having access to the labels of the image. Uh, so some many of the recent self-supervised techniques have focused on instead learning a representation which is invariant to several different augmentations. For example, decolorization or Gaussian blur noise or applying some random geometric transforms or random corruptions. So we hypothesize that the scattering transform can also form a very good pretext task for images or even other types of data, wherein the the task for the self supervised task for the network will be that the network will be trained to predict the scattering transform for the image. The scattering transform, as we know, is invariant to different transformations, and this will help the network learn features which are also invariant, which are similarly invariant to small perturbations. And we believe that that making the network learn such features. So there has been a power disruption. Yes, I'm sorry. I got disconnected. So yeah, as I was saying, we can. Uh, Hello, am I audible, Abhiraj?
Hello, yeah, you're audible. Yeah.
Okay, yeah. So yeah, as I was saying, we can have a network jointly optimize a self-supervised task, which is predicting the scattering transform and its usual supervised task, for example, classification in a multitask framework. So that joint optimization will help the network uh, learn good representations for good discriminative features in addition to invariant features which we hope we hope will be much more robust to perturbations and will be much more general. And such observations have been made for other self-supervised tasks also and for other multitask optimizations also. But the strong property of invariance for the scattering transform will, I think, make it a better choice than other self-supervised tasks for this purpose. Additionally, we believe that scattering transforms can be invaluable for few-shot learning. And few-shot learning is a paradigm of machine learning learn, where we try to train a model to discriminate or to perform its task only by seeing a very small amount of images, as little as five or as little as even one image. Deep learning models are typically not suitable for it because they overfit very badly on such in such cases, and they are unable to generalize because they have a lot of parameters, and training them on such a small number of images will lead to poor generalization. But if we instead use a scatter net to first initially extract features from the image, that would reduce the number of trainable parameters, and and it can be probably be very helpful in few shot learnings or at reducing helping to mitigate the problem of overfitting due to a large number of parameters, and also providing very useful good general features which can be classified with ease instead of relying on very specific features which are extracted from as little as five images. Additionally, another application for scatter nets is that it can be used to provide models some degree of robustness to attacks. So adversarial attacks on deep neural networks are is a very hot area of research currently because convolutional neural networks are being used in a variety of systems these days. But as many might have heard, they are extremely vulnerable to attacks. For example, there have been instances where some invisible noise has been added to an image, which causes network to predict a human as a dog or a human as a pole, which can be very damaging for systems like self-driving cars. So networks should have robustness against such attacks, and scatter nets can help provide such robustness because they are very interpretable, and they extract features in an interpretable way, and they can they can filter out such noise, or such noise which is intended for attacks, and help generate adversarial robustness. So this is one thing which has not been evaluated by current work, and we think that this can be a very good addition to the work which has already been done in scatter nets. So Abhiraj will continue the rest of the.
Yeah, so another direction which we feel that this can be taken is OD detection. So by OD, I mean out of distribution data detection. So recently there has been a lot of discussion in the deep learning community that the current models that we have for our CNNs are produce very overconfident outputs even when the model is not trained for a particular class. So for example, if a model is trained for classifying between cats versus dog, and then at the test time I pass an image of that of a car, say, then it is highly possible that the or yeah, over here I have taken an example of a monkey. So if I pass an image of a monkey, then it is possible that the model will will predict cat for that particular image with very high probability, even above zero point 0.9 point 0.9. So we need to be really robust to we need to have models which are really robust to such kind of overconfident predictions. So we feel the scatter nets could help there in a way such that what the scatter nets are actually doing is giving us some good representational space which is separable in that higher dimension. So what mean by this is, if we are representing the images with with a vector of dimension 1024, then in that 1024 dimensional space, all the images related to one class can lie in n minus one dimensional plane, and this is possible only because of the property of scatter nets of being robust to deformations or any other kind of transformations to the images. So these n minus one dimensional planes can then be taken as the spaces on which our classes that on which our known classes lie. And if we get a class which if we get a sample which is does not which is basically far away from all of these planes which are our in class planes, then with an appropriate threshold on the distance between the feature vector of that and the plane, we can decide if sample is out of distribution or not. So this sounds very trivial for this particular case that we have spoken over here, but when we go to medical domain, so there having such overconfident predictions can be really harmful. The next thing that we think the StatNets could be helpful are StatNets could be extended are to deeper models. So in this in these three papers that we have discussed, the models that were used along with the scatternet were quite simple models like PCA and VGG model. But it would be interesting to see if we get any better results by including these in the ResNet 100, ResNet 101 or ResNet 50 model. So just like the model that was used over here, which was VGG model, this can be changed to ResNet 100 model and see if we are getting better representations. We hypothesize that it should since the model is quite large, the ResNet models, there shouldn't be much of an advantage of doing such an addition of a scatternet layer, but it would be interesting to see if we get any improvements and then analyze why we are getting those improvements. Since and the analysis should be easier for a scatternet case, since we have a good mathematical understanding of the scatternets. Uh, the last thing that the last extension for scatternets we think is possible is to use different types of data sets. So over here we have only considered images and audios, but it would be interesting to see if you could construct similar wavelet scattering transform for different data types, like that of hyperspectral images or time series data. And even in case of graph, if we have a graph type of a structure to our data. So yeah, that would be very interesting to see. Yeah. So to conclude our presentation, we have summarized three papers over here: the invariant scattering convolutional networks, deep scattering spectrum, and learnable scatternet, the local invariant convolution layers. So each of these papers builds on the previous work, and shows that it is achieving better results, and they are state of the art considering the time the paper was published. So they were state of the art at that particular time. And so the base idea that is presented in all of these papers is really interesting, as the features that are obtained from this particular idea of scattering wavelet transform uh, is uh, is method has a good mathematical basis to it, and we can understand why we are getting such features. So this is not the case in current state of the art CNNs that we have, which predicts which give us some representation, but we literally don't have any interpretability to why we are getting those type of features from our model. So we in this paper, we have a reflection paper, we are also proposed a few different directions which the work on scattering wavelet transform could be extended. And we feel that the extensions are quite relevant to the deep learning community today, and will potentially lead to better CNN models in terms of performance, robustness, and interpretability. We also feel that expanding the scatternet invariant convolution to more complex data sets is still a topic of further research. So yeah, with this we conclude our presentation. Thank you for listening. Yeah.